Okay. Okay. Hello, everyone. Thank you for coming to my talk today in such big numbers. My name is Petar Veličković. I am currently a final year PhD student at the Artificial Intelligence group at the Computer Lab at the University of Cambridge, and I'm very thankful to have an opportunity to speak to you all today. I have been thinking, since this is primarily an imaging venue, I've been thinking there's exactly one imaging paper that I have been involved in throughout my 3 years of the PhD. So deciding what to talk to you about today was actually quite easy. And I'd like to start off by thanking all of my collaborators on this work, Guillem and Arantxa from the Centre de Visio per Computador in Barcelona, Conrad from the Department of Psychiatry at the University of Cambridge, Esther Jacobson and Alan Evans from the Montreal Neurological Institute, and Michal Drozdal, Adriana Romero from the Facebook AI Research, and Joshua Bengio from the Montreal Institute of Learning Algorithms. And we have done a project that involves deploying the latest advances in graph convolutional networks to segmenting brain meshes. Okay, so the task that we're looking at is a task of cortex parcellation, i.e. Partitioning different parts of the cortex into functional regions. And we want to do this because different areas of the cerebral cortex are involved in different cognitive processes, such as visual, language, comprehension, and properly mapping them will help us understand how the cortex is organized. A cortical mesh represents a common coordinate system for the brain, and it can represent multiple imaging modalities and features kind of located in a particular region of the brain, and can be used to co-register cortical surfaces between different individuals. I should highlight here that I am a neural network person. I'm not a brain person, so any specialized questions should probably be directed to some of my collaborators. Okay, so previous work towards tackling this problem, there's two particular pieces of related work. The work from Glasser and others, which used a multi-layer perceptron classifier to recognize each of the cortical areas, and they've trained it on semi-automatic labels of cortex parcellation. And the previous state of the art, as much as we were aware, the work from Esther Jacobson from 2016, which compared connectivity templates of each vertex of the cortical surface to parcellate Broca's region. Now, we decided to take an approach that uses convolutional neural networks, in particular the latest advances of convolutional neural networks, which are graph convolutions. These methods generally achieve state-of-the-art on image segmentation, and it's kind of analogous to the task of segmentation on a graph, which is what this mesh represents. And what's really nice about this is we can reuse some of the ideas that work on image processing, such as parameter sharing and data structure exploitation. We do have to put in a bit more effort, unfortunately, but if we're able to put in the effort, we're able to generalize the convolution operator from images to graphs. And the idea is essentially kind of the same. You'd start from a central node in a graph for which you wish to derive higher level features. You look at its immediate neighborhood the same way you'd look at the immediate neighborhood of a pixel in an image. And in some combination of all of these nodes, you derive the next level features for a particular node. And then you can just stack a bunch of these layers together and have a prediction layer which does your segmentation for you. This image was taken from one of my tutorials on graph attention networks, which was a model that we deployed here and that I personally developed. So there's there's many popular ways of doing graph convolutions, all of which have came out from like 2017 onwards. And we have tried two different ways of doing graph convolutions. The first one is the graph convolutional network of Thomas Kipp, or a special case of Chebyshev networks, which came out in 2016. The main idea is when we want to derive the next level features for a node, we will look at all the nodes J that are in node I's neighborhood. That's what the N is for. What we will do is we will take all of the neighbor's features. We will first pointwise transform them, because for deep learning you need to have a linear transformation if you want to learn higher level features. And then we combine them together using some coefficient that links together node I to node J. In the original graph convolutional networks, this coefficient is fixed based on the structural properties of the graph. And once you have these coefficients, you just learn a linear combination of all of your neighbors that then gets passed through your favorite nonlinearity, such as rectified linear. And in the graph attention networks, we decided that basically we're not going to fix this coefficient up front based on the graph structure, because in many tasks of interest, you won't know the graph up front, or the graph may dynamically change. Or in the case of these kinds of mesh images, you don't know the test graphs until you test. So in this case, we actually learn an attention mechanism, which is a learnable neural network that takes features of node I, features of node j, and learns what the coefficient is, rather than fixing it in place. So that's the main difference between these two types of models. Okay, and we have compared these two against a few standard baseline approaches to doing segmentation in graphs. One thing we can do is just drop the graph structure altogether, which is what most previous approaches did. Like before we knew how to exploit the graph structure, we just drop it and just learn to segment each node individually with a shared classifier. Another thing we can do, because obviously there is some regularity in where brain regions get mapped, we could take node average, which is just predict whatever is most frequent in the training set and see how well that performs at test time. And also we can use the global multi-layer perceptron, which looks at all the nodes together and predicts all of their labels together. So this kind of feeds in the entire graph at once and kind of fully connects everything to everything. Okay, so by using these, we can see whether there's any benefit to not exploiting the statistics and whether it makes sense to take the whole graph at once or actually use the graph structure. And you can here you can see a comparison of a few of the properties of these methods. So the node averaging technique doesn't do any learning, so it doesn't have access to any of these information during training. Node MLP, which just looks at point-wise predictions, just has access to the features within each of the nodes. The full graph MLP, which looks at all the graphs at the same, which looks at the entirety of the nodes at the same time, has access to the features, has access to global information, but doesn't have access to who's connected to whom. And all of our graph convolutional methods have access to all three of those. And we should expect them to perform better. The specific task we looked at, because there's currently a lack of label data, is the parcellation of regions 44 and 45 of Broca's region. And we had a data set, which was a manually labeled parcellation derived from the Human Connectome project from 100 different subjects. Each of the meshes has 1,195 nodes with 9 fMRI features per node and 3 possible labels, background 44 and 45. And we also tried to augment the features with absolute coordinates and degree information. And this also helped out a little bit. Because the data set is of limited size, we could use a 10-fold cross-validation to see how well the models perform. We had 8 folds for training, 1 for validation, 1 for test. We train using the standard atom optimizer, and the loss function is either weighted cross-entropy or the dice loss, standard segmentation approaches, basically. So, node MLP performs with a Jacquard coefficient of 38.7 on average, which is actually worse than just taking whatever is the average in the training set. So doing a pointwise predictor isn't really that good. You need to use the graph structure somehow. If you just take the averages in the training set, you get 49.9. And if you take the entire graph at once, you get 51.8. So all of these approaches are actually worse than the previous state-of-the-art of Jacobson and others. And if we deploy the graph convolutional networks or the graph attention networks, we can find that they significantly outperform the previous state-of-the-art and set the new state-of-the-art on this task. And in fact, they perform more or less the same, which means that the graph structure in the brain mesh is quite regular, and therefore there's not a lot of point to learning the individual weighing coefficients. Although, if you look at the individual performance of region 44 versus 45, the graph attention network can perform better on one or worse on the other. But they're more or less indistinguishable and clearly outperform the previous state-of-the-art. And if we further augment them with the coordinate information or the degree information, we can get a further boost in performance. And to kind of give you a visual feel for how good our methods are predicting on this graph, you can look at 2 particular test subjects from the data set. You can see the ground truth parcellation of regions 44 and 45, and you can see how the different techniques perform. You can see that the pointwise predictor, because it has no access to neighbors' information, it just kind of learns to predict in a fairly disjoint manner everywhere. The previous state-of-the-art of Jacobson and others kind of over segments. And the graph-based models are much more faithful to the ground truth compared to the others. Okay, so in summary, we've investigated to what extent graph convolutional networks can be applied for mesh-based parcellation. We've got some pretty good results, setting the new state-of-the-art on this task, and we outperformed all the previous baselines. These are all the references that you might find useful, and thanks for listening. And if you want to check out our paper, it's on this open review link. Thank you.
Thank you very much. I thought that was really fantastic. Just as a clinician, how would I use this on an MRI scan? Is it have you done it on a number of MRI scans on different people?
Yeah. So this basically the brain mesh is derived from a series of fMRI scans, and what we've done is what we've used is pre-processed data from the Human Connectome project, but presumably like all of these pipelines would be in place. So the idea is to go from the scan, turn it into this graph representation where the brain will be represented as a series of these standard coordinates, and then just feed it through our predictor, and that would give a function. Well, in our case, we predicted functional regions, but in reality, you could predict anything at the node level or at the graph level. We're currently looking into predicting some standard metrics like age, gender, or cognitive score based on the entire graph at once. So yeah, like the actual task that you're doing is fairly general once you have the model in place. Yeah. Yes?
So, sorry, does this need structural information and the functional MRI? Does it use both of those? Is this based on the functional?
So both of them. So there are both structural and functional features in each one of these nodes. That's like we had 9 features. I don't know exactly what they were. Cortical thickness and a few others. Like all the details are in the paper. But yeah, the actual just brain mesh is a triangulation of the characteristic positions in the brain, co-located for all the patients in our training set.
This could be used for different imaging modalities, say for like a tissue section, like a H&E image, perhaps.
Yeah, I think so. I think that as far as we can co-locate what's located in a single node, we can introduce any kind of modalities that we want. We can also introduce modalities at the graph level as well. Yeah, shouldn't be too hard. If we're doing a graph-based task, we eventually summarize the entire graph into a flat representation to which we can attach anything we want. So yes.
One question. So all I need to put in is that node and the triangle mesh, right? That's all. That's all this code takes in.
So the code takes in 2 matrices. One is nodes by features, and the other one is adjacency matrix. That's all.
Right.
Yeah.
So the adjacency matrix will be your nodes, position vectors of the nodes, and your triangles. Is that what you mean?
Yeah. Basically, for each node, what are the other nodes that are close to it?
Right.
Yeah.
And then the other matrix was what?
So in each one of the nodes, you can introduce arbitrary features. So for each one of the nodes, you can like take whatever measurement at that node you have.
If you don't have it,
if you don't have it, you can either leave it. You can either do random features, which works well too, or a one-hot encoding of the node. Yeah.
So basically, somebody would use this at the output of the free surfer software, for example, where it does the segmentation for you, right? So it gives you that mesh.
Yeah.
Would that be correct?
Yes.
Thank you. Thank you very much.